Let's talk about nonlinear regression. What is nonlinear regression? Last time we had points and then we found a line, a linear function, which comes as close as possible to these points. And now we say, okay, it does not need to be a line. Maybe we can say which polynomial of degree 3 fits best to the points. So let's write that down. So we have a set of points and we have a set of functions. And the number of points we have is at least the number of functions we have. At least. If it's the same, then it's an interpolating problem. If m is more than n, so let's say we have 4 functions and 10 points, then we have an approximation problem. And now we want to find coefficients alpha 1 to alpha n corresponding to these functions, for each function one coefficient, such that these functions, the first functions times a constant plus the second constant times the function plus and so on, fits best to the points we have. We can also have here a picture. These are the points. And then we try to find a function which approximates these points best. Okay, and how do we find that solution? If we redo the analysis we did in the last video, then we immediately come to the following solution. We can formulate as follows. This problem we can formulate in a slightly different way. Instead of writing that part as we did here, we can reformulate as a matrix multiplication. These coefficients are always interact with the functions in a linear way, so we can formulate that part as, and this matrix does not need to be quadratic. It's quadratic if n is the same as m. Normally m will be larger than n is, and so this is a matrix of that type. And then this is a vector as many input arguments as we have here. Okay, and then this is a vector which has the same size as it has here. Okay, this is the structure of that problem. And in the special case m is n is equal to n, then we have a quadratic matrix. This is a quadratic matrix, and then we have interpolation. That means we can find these alphas such that it's exactly true that we get here these b values. This is not correct for every set of functions. If you're a mathematician, then you can find a counterexample. But mathematically spoken, these functions must be linearly independent, which is normally the case. And being in that structure, we know we want to find alpha, an alpha vector, such that we get here the b, but normally that is not possible when it's overdetermined. And then we found out that if multiplying with the transpose of a, then we get the best solution in the sense of Euclidean deviation. And how do we find that solution? In the last video we did that analysis. It was a 2 by 2, so we inverted and then we multiplied the right hand side and so on. This is not possible in general. This is only possible if we have a set of only 2 functions. Last time it was the function 1 and x, and we tried to find a linear combination of these best fitting to the points. Normally we are in the situation that we have more than 2 functions, and then we are here and no more analysis is possible, but that doesn't matter because we can use a solver for linear systems, and so that's no problem. But if we are in MATLAB or if we are in Octave, we don't have to multiply by A transposed. MATLAB internally does that step when calling that so, and so we can use that command. Okay, that's all we have to do. Let's have an example. Given a set of points, let's use the same points we had last time. Let's say we want to find a polynomial of degree 3. That's our decision to say, okay, we want to find a polynomial of degree 3 fitting these points. Then I tell you we are in the context of that. Why? Because a polynomial is a sum of something times 1 plus something times x plus something times x squared plus something times x cubed. And so we are in that situation. So our functions are, and so we can continue here. Then this matrix A is the first function here evaluated at the points here. So let's concentrate. The first function is the function 1. If we evaluate at these points, always a 1 is returned. This is the 1 function evaluated at these 6 points. So we need 2 more lines. Then we evaluate the x functions at these points. So we have 1, 3, 4, 6, 8, 9. In this case, this set is ordered. It's not necessary that it's ordered. In our case, it is ordered. Now in the third column, we have the third function evaluated at these points. So x squared evaluated here is a 1, a 9, 16, 36, 64, and 81. And now in the last column, the last function evaluated at all these points. So x cubed at point 1 is 1. This is a very special structure. This ones comes from the function 1, and these ones comes from this one, and every potency of 1 is 1. So this is the reason for that. Okay, now the 3 cubed is 27, cubed is 64, always factor 6, 216, always factor 8, 512, always factor 9, 729. And our b vector in our case is these values. And now using MATLAB, we can use a backslash b and we get the coefficients alpha for these functions. Or if we are not in MATLAB or we don't know that this operator has also the functionality for overdetermined systems, then we multiply A transposed times A times something which we call alpha in the moment is A transposed times B. We can do that calculation by hand. We can also do that calculation by hand. But okay, this will be not much fun, so I don't want to do that. If you call MATLAB and do that, then you get the answer. Alpha is the following vector 2.0383. And thus the polynomial fits best to these points. I want to show you electronically. I program something, nonlinear regression. I don't want to show you the code because I want to let that as a problem for you. We can do maybe in the next lecture. And now let's call that, and then we get the following output. This was my input. This is my A vector, the vector of the X values, the vector of the Y values. And then I do something, get the matrix A, and then either by multiplying with A transposed and then using the backslash operator, I get these coefficients, or using directly the backslash without multiplying with A transposed, I also get these values. And what I get on top is the following. If coded properly, these are my points, and this is my polynomial of degree 3 fitting best to these points. In MATLAB there's also a command which is polyfit, and so you can do the work much easier, but I want you to program in the next lecture this polyfit by yourself. And using Excel I can do the following. Here are our points, then insert a diagram, XY diagram, click to the points, right click to one of these points, then Trendlinie hinzufügen in the German version, I don't know the command in the English version, and then show the formula in the diagram, and then you get exactly what we did on our paper and what we did using MATLAB Octave. You get the polynomial of degree 3 fitting best to the values. Let's have a second example. So this is our example 1. It ends here. And now example 2. And now we want to find alpha 1, alpha 2, for example 2 times e to the 5x, or maybe 0.52 times e to the 1.7 times x, and we want to find these alpha values so that these points are fitted best. And now we are not in this context here, because the parameters alpha don't interact in this linear way. So don't confuse that linear with this nonlinear. Here we have nonlinear functions, but we have a linear combination of functions. And that means here we are in the context, we have a linear combination of some functions, and here we don't have linear combinations because here's a times and alpha 2 is in the potency. So we are not in the context we talked about here. And what is the solution? To be honest, it's much more difficult. It's not a little more difficult, it's much more difficult. Remember, we took partial derivatives, and our lucky situation was then we can formulate the system which we have to be a linear system. And if we do the analysis here, then we get a system of equations, but these equations are non-linear, and then we are looking for solutions of non-linear systems, and that's much more complicated. You need starting values, which means you have to know more or less the solution which are you looking for to use this more or less solution to find the exact solution, and all this stuff. We will later talk in this lecture about nonlinear equations and a nonlinear system of equations, and we will see things are really, really difficult and really not easy to solve. So we will get a system of equations, and it's not easy to find the solution. It's not only not easy in this video, and smart people like me know the solution. No, it's a really difficult problem, and it's not easy to find an answer which is in general true. So for every set of functions, we can here try to get the solution, but it will be not easy and it will be tricky, and the tricks we might use are different tricks than we will use if we have another type here. So this is really, really difficult. Believe it or not, it's really true. And once again, nonlinear regression means this function here is not of the form y is mx plus c, but some nonlinear function. This is the headline nonlinear regression. But what we talk about and when we get really satisfying answers is if we are in the situation that we have a really linear combination of functions. So there are two linears, and one times we are not linear, but in the second sense we are in a linear situation. Please don't confuse that. Let's visit Excel and then let's close this video. So here in the German version, let's click to the line of regression. Let's right click, then Trendlinie formatieren, format the line of regression. And then we can say exponential. And then Excel tells us that 1.7042 times e to the 0.01314 x is optimal, but you cannot be sure that Excel optimizes in the sense of Euclidean deviations. Often there are tricks, so you transform the problem to a polynomial problem, but then implicitly you change the metric in which you measure. That means you abandon the Euclidean metric. So this is a wild field, but I think it's important to talk a little bit about that, because in your later life, most likely you will use that more than once. And the normal thing, even for mathematicians, is using Excel. We don't know what is exactly done internally, but we get some kind of a good approximation to the given points. Okay, that was our video to nonlinear regression.